So this is a colloquium for computational math. And it's my pleasure to introduce Michael Littman. So he's our guest speaker from Brown University. So he's been there for a few years. Before that, he was at Harvard University where he was a chair. So Mike is actually a world leader in artificial intelligence and machine learning. So if you don't know him, you'll know him at this point. I mean, he has been program co-chair at AAAI. I believe this was in 2013. 2012. Okay. Also program co-chair at ICML 2009. Okay. And he has also been giving courses online through Udacity. So some of you might know him through his courses. And I was also told by some students that he has also appeared in some publicities. I don't know much about this, but in any case, Michael is known for lots of interesting things, but I guess the core of his research is reinforcement learning, and that's what he'll talk about today.
All right, thanks, Pascal.
I'm going to turn on the board lights.
The board lights. Then no one will be
shining on the screen, which makes it hard to see.
And now no one will be bored because the board lights are off.
Exactly.
Perfect. Thanks for coming out. So as Pascal said, I'm Michael Littman. The publicity thing that you mentioned, I was in a TurboTax commercial for U.S. tax time last year. So that was kind of fun. I don't get to be like on TV all the time, and I was getting called by people all over my life. Like, wait a second, I'd be big on their screen in their living room. Like, I think that's my cousin, and so people would send me mail. Anyway, that was super fun. So the plan today is to talk to you about some of my current work in reinforcement learning from people, where people are giving signals and training reinforcement learning agents. And it occurred to me really at the last minute, Pascal can vouch for this, it might not be clear that everybody is already up to speed on reinforcement learning. So the sort of niche piece of it that I'm working on makes more sense in the context of the problem more generally. So I'm going to start off by talking a little bit about reinforcement learning as a problem, and then focus in on the issues that come up when we try to do reinforcement learning from human feedback. So just one way that I like to think about machine learning in general and the relationship between reinforcement learning and other forms of machine learning comes down to the kind of feedback that's available to the learning system to get better at whatever it is that it's trying to do. And so this is a figure that I put together that tries to elucidate various kinds of splits in the kind of feedback that you might be thinking about when you're creating a machine learning system. So the three different dimensions that I'm trying to illustrate here. One is this notion of sampled versus exhaustive. So you have a learning algorithm that's going to learn, and does it actually get to see examples of everything that it should possibly need to learn about, or does it just get a sample of those and it has to extrapolate from the sample? And so this dimension is very much about algorithms that generalize from examples. Either the system is just told everything it needs to know, or it has to read between the lines. The main split, though, that separates reinforcement learning from other forms of machine learning like supervised learning is this notion of evaluative feedback versus supervised feedback. So supervised feedback is the idea that, okay, I want to build a learning system that's going to be able to, say, recognize images, so distinguish a picture of a scene where it's snowing versus where it's raining. Okay, and so the way we would do that in a supervised setting is we'd give it lots and lots of examples. We say, here's a picture, this is raining. Here's a picture, this is raining. Here's a picture, this is snowing. And we just keep enumerating as many possibilities like that as we can. The feedback in this case, these images along with their labels, they're not exhaustive. It's not like I'm going to show the system every possible image. We're just going to give it examples. So it's sampled, not exhaustive. But it's supervised, not evaluative. It's supervised in the sense that we associate with each picture as part of the training what the right answer is. Now I want to distinguish that from evaluative feedback. The idea of evaluative feedback is we're going to try to train up a system, and it's going to do things like, I don't know, like predict the weather. Is it going to rain or is it going to snow? And it makes a prediction, and then we tell it how good that prediction was. We don't tell it what the right prediction was. We tell it how good the prediction that it made was. So we give it an evaluation, we don't give it direct supervision. So what would that mean? That would be like, you want a student to learn calculus or something like that, and so what you do is you give them problems, and then they give you answers, and you're like, no. So evaluative feedback is a little bit weaker than supervised feedback, right? Supervised feedback says, here's what you should have done. Evaluative feedback is yes or no, or good or bad, or 35. You do the learner does what it does, and then you say to the learning system 35, and it's trying to do whatever it can to make that score as high as possible. So an area in which this has come up relatively recently, and in the news and so forth, is if you're trying to make a computer system that's going to learn to play video games or something like that, evaluative feedback says that we're going to give you the score of the game. Play however you want to play, but you're trying to maximize the score. Supervised feedback says, I'm going to show you how to do it. You just copy me. I'm going to drive the character around in the game, and you should just make the same kind of decisions that I'm trying to make. Okay, so is that sort of clear that the reinforcement learning stuff that I'm talking about lives in the evaluative part of the world? All right. In some sense, this is, it's like I said, the feedback is weaker, so the problem in many ways is harder, but it is more pervasive, right? It is more the kind of problem that, that you're likely to encounter if you have a system where its performance can be judged, but we don't necessarily know a priori what we should have told it to do. So it's a nice general problem, but it is very tricky. Okay, and then I want to make another distinction within the evaluative setting between sequential and one-shot feedback. So one-shot feedback says the system is going to make a decision. So this comes up very much these days in web companies have to worry about this. So they want to make an algorithm that is going to show people web pages that are going to get them engaged or get them excited or get them to buy stuff or get them to click on things. And so it's evaluative feedback in that when someone clicks on a web page, that's a signal that was either that was good or bad. But if they don't click on it, it's not like there's any kind of feedback that says, oh, you should have shown them this web page instead, or you should have put the link in this wording instead. You're only getting a sense of whether the wording that you used was good or bad. But often the feedback itself is one shot. So the system makes its decision, and then the learning algorithm makes its decision, and then it immediately gets feedback as to whether that was good or bad. This is distinguished from sequential feedback, where the idea is like in a board game or something like that, you make a series of moves, and you really don't know until the end of the game whether that was a good idea or not, right? So you lost the game. Like, well, so that not only am I not being told by losing the game what I should have done at each step, but we don't even really know which step it was that caused the game to go badly. It could have been every step, or it could have been just one critical step, right? And so learning algorithms where we actually have to worry about this kind of sequential feedback are formalized in this setting of reinforcement learning. So we've got sequential feedback that's evaluative and often sampled. So it's a tough problem, but again, it comes up in lots of different scenarios. So I'm hoping that's kind of enough of an intro to what reinforcement learning is. Or not. I'll show you pictures of babies crawling because that's always cool. The only thing that beats. So the purpose of this video is to show that babies do this problem. They try to solve this problem of evaluative sampled sequential feedback. They want to get from one place to another, and nobody's telling them how to move their muscles to do that. But they get feedback. They get the feedback of, did I get the ball that I was looking for or not? And one of the things that's really interesting in the case of crawling is that each kid is searching the space of policies independently, and they can come up with different solutions to this problem. This is one of the things that's cool about evaluative feedback versus supervised feedback, is you don't tell them how to crawl, and they can come up with really cool things on their own. Not necessarily cool things, but like creative things, let's say. I don't know what that was. These are mostly family members and friends, by the way. I really like this one in particular because there's something very symmetric about it. One thing that you notice in all these videos, and I didn't notice this until I compiled them all into one place, in every single case, the kid is trying to go someplace. There's something at the end of the path. They're not just experimenting with motion. They're trying to get the ball. They're trying to get to the high chair. They're trying to get out the door. It's always very directed. And so this evaluative feedback tends to have that kind of property to it, that it's goal-driven. Oh, so one of the okay, anyway. This is the maybe worst one. So Joni had the problem of coming up with a form of locomotion that has sort of kind of parity issues. So she could get from place to place, but not always in the right body position. So she got to the ball, but when she was at the ball, she was upside down, and by the time she got right side up again, it was out of reach. So there are better and worse ways of doing this. And in the case of these kids, they're all older now, so they all managed to get a better solution and can get around, and they're doing just fine. All right, but anyway, we can do the same kinds of things with robotic tasks, but I thought it would be fun to maybe do it as a task like with you guys right now. So, let's see if I can get this to work. All right, so here, it didn't actually get bigger, but the hope is that at least it blocked some of my personal stuff. All right, good. All right, so this is a reinforcement learning environment. You guys are now reinforcement learners, and the issue in the way that these problems are often set up is you get to know what the state of the world is. This is the current state of the world. You get to know what actions you have. You've got, just for simplicity, up, down, left, right, A, and B. Those are your 6 choices that you can make on each step. And then we have this kind of conversation. I'm the environment, you're the learner. The way that the conversation goes is I show you the state, you tell me an action, the environment then implements that action in the world, you get to see the new state, and I also tell you what your reward signal was for that. And in this particular game, or environment, there's no reward for anything except for solving the game, at which point you get a +1. All right, so that being said, go. What would you like to do?
Down.
All right, so but just take a moment to appreciate what you learned from that very first action. Presumably you didn't know what was going to happen, and now you probably have a pretty good hypothesis as to certain things. Like what would left do now? Probably nothing. Yeah, very good. So the dozens of times that I've actually done this with people, no one's ever tried left. And it could very well, but you don't know that nothing's going to happen, but you have a pretty good guess. And in fact, nothing's going to happen. So the next thing that was called out was up. Okay, so that's what happens there. A. Okay, A. That was A. All right, up. Right. I heard right. Oh, I heard up too. Up. Left. 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 A. Okay, A. Done. B. Done. Down. Down. Right. 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 Wrong. Okay, up. Up. Okay, again, take a moment to ooh. Okay. B. B. You guys are very systematic. I appreciate that. A. I heard A and down. I'm going to do A, and now I'm going to do down. Again, take a moment to appreciate. All right. Left. Left. What'd you say? Up? Down. Left. Up. Left. Up. Success! All right, so there's 500 states in this particular MDP. There's 500 different configurations that you could be in at any given time. And you didn't even have 500, like you didn't visit all of them. You from this sample, from this sort of examples that you saw, plus probably a decent amount of background information, and I'm pretty sure some people here have played video games before, and I'm pretty sure you brought that to bear, you were able to figure out how to navigate in this environment. So for those who maybe weren't so quick about it, what happened is, well, this is known in the literature as the taxi problem. This is a taxi. You can tell because it's orange. I don't know. And so you were driving it around in the streets of, Kitchener, I guess. So the north, south, east, west were navigating you, the taxi, and A and B, where A is pick up the passenger and B is drop off the passenger. So this is the passenger. So we navigated over to the passenger, and we picked it up, and now it was in the taxi cab, which I showed by having the circle be smaller. Now when we move around, the passenger stays with us, and we have to drop it off where it wants to go. Where does it want to go? Green. This one wants to go to green. The other one wanted to go to red. Yeah, so the color of this actually tells you where you should go. You navigate over to green, drop off, and you win. So with very little actually interaction with this game, you were able to work out what the dynamics of it were. And in a sense, this is kind of at least one way of conceptualizing the reinforcement learning problem. You're trying to figure out what things do in the world to figure out what actions to take to guide you to beneficial states. All right, so how do we do this with computers? One thing that we do is it wasn't true in, oh, it's not up there anymore. It wasn't true in this game, but often the transitions themselves can be stochastic. So you might try to do action A, and maybe there's some probability that the passenger runs away or something like that. So actions don't always have exactly the same effect, even in the same state. So we have to generate strategies or policies or plans that are optimal even in the face of these stochastic influences. And so typically the way this is done is by solving a set of equations that are known as the Bellman equations. So this is the Bellman equation up there, the Q star. And what we're doing is we're saying we're going to associate with every action that you could take in every state, we're going to associate a quality or a goodness value to that, a value that consists of, well, what's the immediate reward we get for taking that action in that state, plus what good things happen after that. Right? And the way that we measure that is we say, well, sum over all next states that we might end up in. The probability of ending up in that state, the TSAS prime, is the probability if we're in state S and we take action A that we'll end up in state S prime. Okay? This was a deterministic function in the game that we just played, but in general, it could be something stochastic. Once we get to state S prime, now what do we do? Well, we should choose whatever action is best, whatever action actually has the highest future reward. So that's max A prime of Q star S prime A prime. All right, and so of course this is kind of circular because we used the value at the next state to define the value at this state, but the states could actually be talking to each other. There could be cycles and so forth. So there's various ways that this can be solved. One is by iterating this equation over and over again. In the limit, it converges to the solution. There's other algorithms like policy iteration that say, well, we're going to guess a way to behave, and then we'll say, okay, well, what values do we get if we behave that way, which you can actually compute exactly. And from that, how can we actually improve the behavior? So this sort of iterative process of improving the behavior and estimating the values. And there's another way you can do it, just set the whole thing up as a big linear program, and then it just gets solved. All right. So these are kind of reinforcement learning ideas. Actually, they're not, though, because in this setting, in the way that this is being described here, we'd actually have to know how the environment worked in advance. Or maybe we can explore the environment and get to know it, but we might not be able to know it perfectly. So there's multiple families of reinforcement learning algorithms. Reinforcement learning algorithms use as their starting point the experience that they've had interacting with the environment. So they get to observe things like, oh, I don't know, I was in some state and I took some action, I got some immediate reward for that, and then I observed where I went next. That's my information about how the environment works. And I can continue to take actions in different states and collect more and more of that data, but that's the data that I have to learn from. How can you learn from it? Well, there's kind of two families, well, there's three families, but I only illustrated two of them. In model-free learning, what you do is you say, let's take this information, these tuples of experience, and use them to directly estimate the Q function, this value function or quality function. And then we can use that to act by always taking actions that maximize the Q values. And then there's another approach, which is kind of more like the way I was describing what I think you guys were doing when you were playing the taxi game. And that is a more model-based approach where you use this experience to hypothesize how transitions and rewards worked, and then you plan. You actually use that information to decide, okay, well, what action should I take to maximize my reward, and then you act based on that. A third class of algorithms are called policy search algorithms. In policy search algorithms, you postulate a way of behaving, and then you behave according to that way of behaving, and you use the experience that you've gotten to try to improve that way of behaving, which often involves estimating the Q values of the policy that you're actually following. All right, so here's Q-learning on one slide. This is a model-free approach. And what's cool about this, one of the things that's cool about this, is that given a tuple of experience, the update that you make when you're running Q-learning is one line of code. It's like you can't not implement this algorithm. You're like compelled to implement this algorithm. And so the form of it is just we update our Q value for the state action pair that we just experienced by taking the reward we just experienced and adding it to our estimate of what the value of the state that we ended up in is. Take the difference between this, which is an estimate of what the future reward is, and this is what our guess as to what the reward was, and that's our error signal, and we update our estimate a little bit in the direction of that error signal. So it's super cool, and it really works in the sense that you can run this. Lots of cool examples have been implemented with this idea. It provably converges if you decay the learning rates at the right rate. And as I said, it's very, very simple. So with that as kind of prologue, what I want to do is say, okay, how can we actually use this kind of framework to train these agents ourselves? So yeah, so imagine that we've got some kind of, I don't know, robot dog or something that lives in the house with us. I have one of those, except it's not a robot. And you want it to do certain things, like jump through a hoop. Not exactly clear why that's a super important thing, but I did make the dog that lives in my house do that, and it was fun. So the way that you train dogs and other animals, maybe kids, but you need to be careful about that, is through this sort of reward and punishment sort of thing. So you give the dog the opportunity to do something, and then you get to be the reward function. You get to give treats, or you can scold or whatever, but you're trying to influence the behavior, trying to get it to actually improve. And so one story could be, well, Q-learning can do that, right? If we just change this reward so that it's not coming from the environment, it's actually coming from me, the trainer, then everything should be good, and we should be able to train agents to do whatever it is we want them to do, if we're sufficiently patient. Because a lot of these algorithms actually take tens or hundreds of thousands of trials. Which gets boring. All right, but that being said, what I'm getting at is this notion of training from a user, the role that the user plays in actually creating behavior, and what I want to talk about, what I spend the rest of the block talking about, is ways in which this doesn't work out and what we have to do differently to make it work out. So the main thing that I want to get at first is the following notion. So there's a couple ways in which, if you actually literally do this, you create an experiment where you give people access to a kind of a video game, and there's a little agent moving around in the world, and the person's giving reward and punishment to that agent to try to influence its behavior to be a certain way. How does this work out? It turns out it works out really badly, and there's a couple reasons why that this happens. And so I want to talk about what some of the reasons why are and how we can actually get around them to make agents that really can learn from human feedback. So one of the things that we know, on this slide I'll talk about two of them. One of the things that we know is that people, when we ask them to give feedback to an agent, tend to give feedback on the individual actions. They tend not to give feedback that looks like rewards. And so the evidence for this is from a graph from a paper by Brad Knox and Peter Stone, is that they actually had people train an agent to kind of go through a maze and try to get reward. And they found that if they set the discount factor was this gamma, this thing that controls how much future reward counts relative to immediate reward, that if they set this to close to 1, so that the future reward matters a lot, so it's actually trying to maximize total reward over the run and not just sort of immediate stuff, mostly the agent never reached the goal. And in fact, the smaller they made this discount factor, the higher the probability is that they could train the agent to do what they wanted it to do, until the best results that they got were with setting the discount factor to 0. Essentially, ignoring the fact that the agent is thinking about the future at all, just giving it direct feedback about the action that it just took. Which really seems like unfortunate, right? It's actually taking away a lot of the interesting sequential aspect of training a reinforcement learning agent. Another thing, so that's bad, but another thing that's probably worse is illustrated by this graph that comes from a paper by Charles Isbell and colleagues, where they had an agent in a shared environment, and people were allowed to give feedback to that agent to try to get it to do things that they wanted to do. So it was a very similar kind of setup. What they found is that as time went on with people interacting with this agent, the feedback that they gave, both positive and negative, decreased. So the longer the agent was in the world with them, the less likely they were to give it any kind of feedback at all. Now, part of this is maybe they got bored, but part of it, I think, is something deeper and more important, which is that as the agent was actually getting good at following their instructions, doing the sorts of things that they wanted, people didn't feel the need to keep rewarding them for that. It's like, good, you've got that, I can move on. The problem is that these reinforcement learning algorithms are expecting that reward to happen all the time. And if you withdraw that reward, they start to freak out. And they freak out in a particular way. They freak out by saying, I estimate that the amount of reward that I'd be getting for this kind of behavior is up here. The reward that I'm actually getting is down here. I need to search for a better way of behaving that gets me back up here. And so they start to unlearn everything it is that they learned because they're not getting feedback for what they had learned anymore. So this is bad, right? So this means that essentially the kind of feedback that people give results in these algorithms learning good behavior and then unlearning that behavior and getting really dopey, all right? Which is not what we want if we're trying to train these agents to do things that we want. All right, so those are two examples. I've got more examples. This is a study that I did with David Roberts and some of his students and other colleagues. David is cool because he's a computer science professor at NC State University, and he has a dog. But not just a dog, right? He has a dog that has a cool computer science vest on it, but that's maybe not super relevant now. But he actually is a dog trainer. So he actually spends time training dogs and then taking them out into the woods and participating in, I don't know, whatever dog training competitions they have. But he really knows this dog training stuff. And he's pointed out that, in fact, he personally is not at all surprised that reinforcement learning algorithms, as they currently exist, can't be trained the way that we train dogs, because there's a conceptual mismatch. And so in this study, what we focused on is the question of what does no feedback mean? So we created a really simple little game, and we recruited people to play this game. And the game went like this. We're a trainer, and we're trying to train our dog. This is a little dog in a field. We're trying to train our dog to patrol the field. And in particular, what's happening is the field is, on every time step, it's being attacked by, I don't know, rats, some kind of critter. It's coming to the field. And what we want to train the dog to do is run at the rat, and then the rat will run away. If anything else that it does will cause the rat to get into the field, and that's bad. So the way that the game is played is a rat appears, then the dog moves in some direction, and then the person playing the game provides feedback. Was that, positive, negative, or nothing? My guess, the way that I would play this game, is to do what I think is the obvious thing, which is if the dog moves in the direction of the rat, then I give it positive. If it doesn't, I give it negative. This is simple. That's not what people actually do, for a bunch of reasons. What we actually see people doing a lot of people do that. This is, you could call that the explicit reward, explicit punishment case. And in fact, a lot of the subjects that we recruited really did do that. So when the agent did what they wanted it to do, they gave positive, and when it did something that it didn't want it to do, they gave negative. But even more people were in this other box. This is the box of explicit reward, implicit punishment. So when the little animated dog did what they didn't want it to do, they didn't provide any feedback. Now, it turned out that one of the big reasons for this is that the people that we recruited, a good chunk of the people we recruited, are professional dog trainers. So David used his social network to bring these people in. And the understanding among dog trainers is you don't want to give punishment. Punishment is a really dangerous thing to do when you're trying to train a dog, because it causes them to kind of shut down. It causes them to not want to learn anymore. They just want to avoid the punishment. And so if you're giving explicit punishments, you could end up teaching the dog basically to not want to play the game at all anymore. like this is a no-win sort of situation. I'm just going to shut down. And so they are very sparing with their punishment. And in fact, what most of them did is they just didn't use it at all in the game. So for them, not giving reward was supposed to be taken as punishment. Like that's the thing you want to try to avoid. Very few people did this, which actually is probably the best way of training these agents, which is explicit punishment, implicit reward. So when it does the wrong thing, you smack it. But when it does the right thing, you're like, okay. So we didn't see a lot of people do that, but the algorithms actually really like that kind of feedback. They tend to do well with that feedback. And then 3 subjects on Amazon Turk gave the implicit reward, implicit punishment case, which is the dog does whatever it does and the person doesn't pay any attention. That turns out to be an extremely ineffective way of training the agent. All right, so what we found is that we actually needed algorithms that not just responded to the rewards and punishment, but also to the absence of reward and punishment, to put some interpretation on that information so that it could learn more effectively. And so what we ended up doing is focusing on algorithms that use human feedback not as a quantity to maximize, not as kind of an economic incentive, and you're trying to push that profit motive, but as a kind of evidence, as a kind of communication signal, right? So if the person in the experiment, the trainer says, good, then what that is taken as is evidence that the action that the agent just took is the kind of action that would happen if it were following the optimal policy for whatever task is in the trainer's head. So now we explicitly have a notion of, what do they call it? It's kind of a mind-reading-y kind of thing. That's what psychologists sometimes refer to this, a theory of mind, where the learner is not just, okay, I'm responding to the economic incentives, I'm trying to maximize my reward. The learner is thinking, I want to do the task that's in the head of the trainer. I don't know what that is. But when I get feedback, that's giving me some evidence. It can actually change my Bayesian probabilities with respect to all the different possible tasks that I think that the trainer might be trying to teach me. And so reward is taken as evidence for the tasks that are consistent with the action that was just taken, and punishment is taken as evidence against that, right? So any task that I think that the trainer might be getting me to, or trying to get me to learn, if the action that I just took is punished, then any task in which that action would have been the right thing to do, that should be downweighted. That the probability of those should be decreased. And so one advantage of this particular perspective is that it really does focus the question, it gets rid of this notion that we're trying to maximize reward and gets more towards the notion that we're trying to convey a task from the teacher to the learner. But it's also very nice because once we're in this Bayesian setting, we can also factor in things like the trainer style itself. So we can say, okay, there's some probability that this is the kind of trainer who gives implicit reward. There's some probability that this is the kind of trainer who gives explicit reward. We can factor those pieces of information in when we do our updates on what the possible task is. So it gives a very nice kind of unified framework for thinking about how to use the feedback that the learner is getting. We do that, it helps, so that's good. It is able to actually learn from nothing effectively, so it can actually learn once it figures out, oh, you're the kind of trainer who nothing means good, or nothing means bad, now I can start using that information to learn more quickly. So that's pretty cool. All right, so the next issue with human reward that I want to get at is this notion of positive reward cycles. So this is another experiment that I was involved in. This was by Mark Ho and some other colleagues at Brown, where what we did is we gave people, this is kind of a cooler interface and a cuter dog. We said, we want you to train your dog friend to get to the door, to come into the house, but without tromping on your nice flowers. Okay, so that's what we told them. And now we said, your job is now to give feedback to the dog so that it'll learn the right thing. And so we illustrated the dog taking various kinds of transitions in this world, and then we asked the people to choose, reward, like, good dog, or really good dog, here's some treats, or bad dog, a little scolding, and, really bad dog, we're going to shock you. No animated dogs were shocked during the course of this experiment, but we just wanted to have kind of a scale. We didn't want to put numbers on it. We wanted to give kind of a, serious positive, serious negative, mild positive, mild negative. And so we had people do this. We collected all the rewards that we got from them, and then offline, after the fact, we said, okay, what would the behavior be that would maximize, like if we treat these as actual numbers, what would be the behavior that would maximize the expected reward? And what we found is that their trained dogs tended to do things like this. They tended to get out of the flowers, walk along the path, get just close to the door, and then jump in the flowers. Then jump out of the flowers and walk along the path, and then jump back into the flowers. They would go around and around and around. So why are they doing that? The reason that they're doing that is because people, not surprisingly, were giving positive reward for walking along the path and negative reward for getting in the flowers. And the dog, rightly reasoned that you can engage in arbitrage. You can actually, by walking along the path, you're getting lots and lots of profit, and then you pay a little bit for stepping in the flowers, but what you pay for is the opportunity to get a lot more positive reward by going along the path again. Okay, so they do this calculation that says a little bit of punishment could get me a lot of reward, and then they go around and around and around. So, and that wasn't, like one or two of the people, that was like almost all the people. So the fraction, this is a histogram of the value of the cycle that the dog found from the feedback that the people gave, and everybody, except for these two people, everybody was generating behavior that had positive reward cycles in it. You sometimes see this with kids too, where they'll do the calculation of like, I know I'm going to get punished, but man, this is going to be awesome. You really don't want to be in that kind of situation, because it really is very difficult to set up the incentives just right, so that if behavior is optimized with respect to those incentives, it's the behavior you actually want. You really want agents that are trying to figure out what you actually want and do what you actually want. But anyway, in this case, these kinds of Q-learning or reinforcement learning agents were mostly going around and around and around. Yeah, well, so teenagers they start to kind of cotton on to this idea that, wait, I can actually plan ahead a little bit, and I can take a little bit of punishment and gain. Yeah. But there's some toddlers who do this too. My daughter, as a teenager, has been pretty good about doing what we actually want. But when she was little, man, she'd like put her hand on the thing and then look at me. Like, is this going to be worth it? I'm going to learn something from crashing this, but he's going to be upset. He's not going to be that upset. Bam. And like eye contact the whole time. I'm like, I'm living with a sociopath. But anyway, it turns out she's awesome. But like, I was really afraid for a while. All right. So again, how are we going to address this? One way that we can address this is with the same perspective that we took before, which is now treating these feedbacks that people are giving when they're in the experiment, not as numerical things to be optimized, but as feedback about the behavior that's being taken. And so we can use this same kind of approach, this Sable, this Bayesian learning approach that I described before. And so we had another experiment. So after that first experiment where we just had people provide the feedback, but the dog was walking around more or less randomly. We just wanted to sample the space to see how people were providing rewards. And we saw that most people were generating these positive reward cycles. And I thought, okay, but if you actually see the dog behaving like going around and around and around, people are going to be like, oh, I see, I need to change my feedback, and they're going to fix it. So that turns out not to be true. So we did the experiment of having them actually train a learning algorithm, not just giving the feedback to us and we do it offline, but literally while they're playing the game, the agent is changing behavior in response. And we looked at 4 different algorithms. We looked at a Q-learner that is a model-free reward maximizing agent. We looked at a model-based maximizing agent that's actually trying to figure out, okay, here's what all the transitions in the grid look like. Here's where the rewards are that I've been given so far. I'm going to adopt a behavior that maximizes those, versus ones that are actually doing action feedback, this kind of Bayesian idea of estimating what the trainer actually wants and then taking that as their behavior. And what we found is that after 8 or 9 training episodes, these red algorithms, these action feedback algorithms, were taking fewer steps to goal. They were actually, the dog was going directly to where it needed to go, whereas the more traditional reinforcement learning agents were running into all sorts of trouble. They were taking a long time to get to the goal. And in fact, this is because we cut off the reason this is not infinity is because we would cut off the episodes. So the average length of the episode was high, but it's really even higher than this. And in fact, what you see people do, again, unlike what I thought they would do, which is they'd figure out, I'm sending it around in a cycle. One way to fix that is don't give any positive reward at all. Only give negative reward. So as long as it's following the right path, do nothing. And if it's following the wrong path, then bing it. There'll be no positive reward cycles because there's no positive reward. It's, mean or something, but it sends exactly the right signal. that's not what happens. People see it going around in a circle, and they're like, I need to fix this. And so as the agent is starting to do the right thing, they just pile on more reward. Like, yes, yes, that keep doing that. And then it jumps down. It's like, no, that's not what I mean. And so they know that something's wrong, but they can't for the life of them figure out how to undo it. And it's sad. All right. On the other hand, we had people training the Sable algorithm, and not only in that little environment, we did a more complex set of MDPs, or Markov decision processes. Like we asked people, train the dog to move the red bag to the blue room. So there's a little dog, and it moves around in the grid, and when it bumps into objects, they kind of push ahead a little bit. Over 90% of the subjects that we recruited were able to actually train the dog with reward and punishment with this kind of Bayesian algorithm to do the right thing. All right, so there's, let's see, how am I, is that literally the time?
Yeah.
We're going to get kicked out soon, I think.
There's a class in here at 11:30.
Yes, all right, so I'm going to tell one last short story, and then I'm out. All right, so this last little piece that I think is really neat is that the way that I've described things so far is that the feedback is with respect to the behavior of the agent. So that we're imagining, or the learning agent is now trying to imagine that the feedback is based on their performance. What we actually find is that people base their feedback on relative performance. So we did this following really simple experiment. We said, here's a smaller version of that same flower bed kind of task. We've got a dog. We want it to go to the door without stepping on the flowers. And we show people, this is what the dog knows how to do now. And we animate that. And then we say, OK, now we're going to do that again, but why don't you give it feedbacks to push it in the better direction. So the optimal policy to take is start off with that red arrow and then go across and come down. Going the blue arrow means that you're tromping through the flowers. Going the green arrow means that you're maybe going around too long, like it's not taking a shortest path. When we show people the agent, we're going to show people the agent behaving in some way, and then we're going to show it following the green arrow and going around. And we want to know what feedback do they give to the green arrow. And it turns out that if we showed them the agent performing optimally, so following the red arrow and around, they would take the green arrow, that behavior, as being bad. Right? So the agent was doing the right thing, but now it's doing the wrong thing, so we're going to punish it. On the other hand, if we had shown them the agent walking through the flowers and then it takes the green path, they see that as good because, OK, you've learned to avoid going through the flowers, that you're headed in the right direction. And so the feedback is actually dependent not just on the behavior, but on people's guess as to what's in the head of the agent. And so from that perspective, you really want a learning algorithm that can do that can actually learn with respect to heading in a direction from where it currently is. And what we found is that this is a really great match to a standard algorithm in reinforcement learning called actor-critic. And what we're able to show is that we can get a convergent algorithm for that kind of feedback by building on top of those ideas. And this is not a video. OK. But if this were a video, what you'd see is that we can use this idea to actually train this robot to follow a pink ball around and various other kinds of tasks where the tasks are chosen entirely by the trainer. In this particular case, the experiments that we've run so far with the robot have only been with James McGlashan, who's the postdoc who wrote the code. So it's maybe not so surprising that he's a robot whisperer and can get it to do lots of different things. But we're in the process now of trying to scale this up and run some experiments with regular people training our robot using these kinds of approaches. And so we're optimistic that we're going to be able to make a better connection between regular people and the agents that are in their world. Thanks.
So in dog training, it's a common belief that you train a dog, but the dog also trains you. Do you also see that in your experiments?
So it's certainly the case that the people in our experiments are learning something, and there's better and worse ways of the agent giving them feedback about what they're doing that people can pick up on or not. But we're really just starting. This is a question that didn't occur to us for a long time, but it's just dawned on us, and we're now worried more about than we were about feedback from the learner back to the teacher. We were mostly thinking of as the learner as being fairly passive in this process, but I think you're right. I think it's really important to think about that two-way communication. Yes?
Is there any work on training agents in such a way, not from one person per se, but from like a crowd of people at the same time? they might have like different ways of decreasing their reward over time.
I see. So if from evaluative feedback, I want to say no. I think that there have been experiments where a crowd uses supervised feedback to train various kinds of machine learners. But in terms of evaluative feedback, I think you're right. I think it becomes a harder problem because now you've got a mixture of feedback styles. And if these people are saying no feedback means good, and these people saying no feedback is bad, and now the agent's like, I got no feedback, I got no clue, right? I have no idea which direction to go. So no, I haven't seen that. That'd be funky. That'd be fun. At the moment, so far, the tasks that we're looking at are still pretty simple, that are on the time scale that individual people can do it. We're thinking about crowd stuff more from the perspective of if lots of people train their individual agents to do specific tasks, can we pool that knowledge together in such a way that now a new person could train an agent to do a new task even faster because we already know the kinds of things that people tend to train. That's the direction that we're headed first, I think.
So you slightly mentioned that gamma should be set to 0 that compensates certain behaviors. Has there been any attempt to have a dynamic gamma where it's set to 0 at the beginning, sort of like for a baby where everything is rewarded, and as it goes on, it looks forward into the future more?
So the work that I was citing there by Knox and Stone, they did do a bunch of clever things with gamma. I don't remember if adaptive was quite one of them, but they did notice that setting it to 0 is good in some cases, but it's also bad because you can't get you actually have to teach it about every single individual state. It can't generalize. And so they had clever ways of actually bootstrapping that. I forget how they did it. We think a more direct thing is to avoid the whole reward optimization thing entirely and view it as a task estimation or communication problem. Top?
So here you're trying to get people to give agents directions in such a way that it works with the algorithms. Is there any information for how you might do the opposite, like get the algorithms work with the directions that people already do?
So could we? I translate that as could we train people to train Q learners? Is that?
Could you try to do something that's a variation of Q learning that works with like the directions that people already?
Oh, but that is what we're trying to do. We're saying people train how they train. Can we make algorithms that use that feedback effectively? So that is what we're doing. Okay.
The other thing I wanted to know that the value of the feedback, either punishment or the rewards, are equal part in the fix during the learning, or is changing?
So.
Because, for example, if somebody gets the reward and at some point it does good things but didn't get a better reward, but if it goes back to punishment, has the previous punishment, it may prefer to do better things than going back to the punishment.
So maybe you're saying, like, do we want to interpret the numeric values differently depending on context in some way? I don't know. We did do one thing though. We were worried that maybe our interpretation of how they were giving numbers was different than their own interpretation, and so we did do a study where we actually said, how many punishments is worth a reward? How many rewards is worth a punishment in your scale? And people, under the interpretation that people wanted us to take, we were still getting positive reward cycles. But I don't think we looked at this question of, well, maybe in the beginning we should treat them as being, high magnitude and then later as lower magnitude, or a punishment that comes after a reward is different than 2 rewards in a row. Yeah, I'm not sure. That's worth thinking about.